As you can see from the title of this video, this tutorial is about the dissolving process and properties of solutions. To this point in class, we have started to classify mixtures into three different categories: solutions, suspensions, and colloids. Now that we have decided what makes up each of those types of categories, we're going to focus in a little bit more on solutions in particular, because they're the most commonly used in our branch of chem. When something dissolves, right, we have to talk about terms. Right? And one of the terms that we're going to talk about, right, is the solute. If you remember, the solute is the thing that gets dissolved. The second aspect of a solution is the solvent. The solvent does the dissolving. And most often the solvent is H2O. It is known as the universal solvent. But I'd like to get a little more specific about how that process occurs. How is it that water, for instance, as a solvent, can attack the solute and get it broken down? Taking a look at some things we've seen before, what I have here in front and what I have behind me here is an example of a salt crystal lattice, an ionic compound that has positive cations and negative anions, right, in a crystal lattice structure, all held together, right, with very strong forces. If we are going to get something to dissolve, we have to find a way to break individual ions off of the crystal lattice. And how that occurs is displayed up here. Here is my crystal lattice. The large green spheres are negatively charged particles. And the smaller spheres are positively charged cations. So for instance, NaCl would be a good example of something that would look like this, salt, which we know dissolves in water. Then what happens is an H2O molecule comes along. And when that H2O molecule comes along, because it's polar, it has an uneven charge, we have the negative unshared pairs of electrons on the oxygen and a partial positive charge on the hydrogen, due to the uneven sharing of the covalent bond. The partial positives of water are attracted to the negative of the cations. Rather the anions. So what happens is a lot of waters will come up and bind themselves to that anion, and eventually, if enough do it, what results is what we called a hydrated anion. And the hydrated anion has your negatively charged piece of the crystal lattice and a lot of waters that it took to bind to it and get it to remove. And if you notice, as this happens, the same thing in reverse happens with the cation. Here is my positive cation, so the negative end of the water molecule, the part with the unshared pairs of electrons, will attack the cation, and we will get a hydrated cation. As that process continues over and over and over again, notice what happens to the crystal lattice. It tends to get smaller and smaller and smaller, and visually that is what we would see if we put a cube of salt into a glass of water. Eventually, it would get so small, right, that the water would overwhelm all of these, breaking off every piece of this to the point where we would no longer see them because they were individual ions. Right, so that's how the dissolving process occurs. Right? Water molecules or the solvent, whatever it is, will attack whatever the solute is, breaking it down into miniaturized pieces. When that happens, there are a couple different things that can result with the solution that's created. One of the more interesting characteristics, right, is that sometimes solutions have the ability to conduct electricity. And that gets into a discussion of electrolytes and non-electrolytes. Using the prefixes, right, electro, non-electro, right, some solutions are able to conduct electricity. Electrolytes place ions in solution and conduct electricity. Non-electrolytes do the opposite. They do not place ions in solution and do not conduct. So the idea is this. It tends to favor that the solutions that have ions are the ones that have the ability to conduct electricity. Because you need ions in solution for the negative electrons to be able to move through, ionic compounds make the best electrolytes. Things that do not break into ions in solution, like covalently bonded compounds, more often than not, become non-electrolytes. All right, a good example of an electrolyte would be something like any salt, right? Because all salts, a metal with a non-metal, are ionic compounds. A good example of a non-electrolyte would be sugar, C6, H12, O6. A glucose solution would not be a good conductor of electricity because this this molecule will dissolve, but it will not dissolve to where it produces ions, therefore it can't conduct an electric current. To show you this in a more visual fashion, up here, there are 3 light bulbs. Right? One of the light bulbs is out. One of the light bulbs is dim or dimly lit. And the third light bulb is bright. The setup of all of these is the same. What we've done is we've run a wire up to the base of the light bulb, which from a DC power source, some type of battery, will provide electrons. Like if we can complete the circuit, the light bulb should light. So the idea is if the electrons can move up through the light bulb, back down through the filament, and then pass through the solution down here, right, they could complete the circuit if the solution conducts and the bulb will light. So we end up with 3 results. Like the first result, if I drew a picture of the ions in solution down here, right, is out. That means here we have no ions in solution. Right? No positives and negatives. It would simply be all molecules with no charges. In the dimly lit one, a current and a electric flow of electrons, can pass through, but not very well. That means there are some ions. And this would be termed as a weak electron. Right? The last type is very, very brightly lit. Right? That means this solution here must have many ions, and this would be what we call a strong electron. Now, don't get this confused with something that's creating electricity. It's not an oxidation reduction reaction, but it does have the ability to conduct electricity. Right? So that's the second thing that solutions have the ability to do, right, is conduct electricity, right, after they are getting dissolved. Right? The last thing I want to talk about is the types of solutions that we can get and how we can make those solutions become dissolved more quickly. When you dissolve something, there are 3 different states that a solution could be. And they're all referred to types of saturation. So I have 3 beakers here. Whenever I try to dissolve 2 things, I throw a cube of, say, sugar or salt into one of these beakers. Right? The water molecules, like we talked about, will attack that cube, trying to break pieces of the crystal lattice apart or of their covalently bonded network. Then, when the water is done dissolving it, or if it can dissolve it, the water has carrying around with it these hydrated ions. Right? So is there a limit to the amount that the water is able to hold? And yes, there is. Right? The 3 types of solutions that we'll get are unsaturated solutions, saturated solutions, and super saturated solutions. Okay, with the types of saturation with the solutions, right, water molecules will attack the cube of salt. Now, so long as there are still water molecules that do not have, okay, particles attached to it, right, it is called unsaturated, because even if this cube were to go away, I could put more sugar or salt in and the water would be able to dissolve it. Right? So as long as there's still enough waters to continue the dissolving process, it is referred to as unsaturated. A saturated solution would be one where we have dissolved as much of the crystal as we can, but every water molecule is holding the maximum amount of solute that it can. So what would happen here is all of these waters are filled up. It wasn't enough to dissolve the crystal cube that was in there, and if I dropped more, a solid piece would fall through because the water is no longer able to hold any additional solvent. You see this all the time when people over sugar their iced tea. You get a big amount of solid sugar at the bottom that couldn't dissolve because the water that was making up the tea was holding the maximum amount. A way to convince the waters to hold additional solute particles would be to supersaturate it. And most often, we do that through a temperature increase. We give the water molecules more energy by increasing the temp. And now, instead of being able to hold, say, 2 different solute particles as I depicted here the whole time, we convince them all to hold 3. Which means that now we might be able to dissolve our entire cube of sugar. So you get saturated, unsaturated, and supersaturated particles. Okay. The last thing I said I wanted to talk about is how quickly it takes something to dissolve. Right? And there are things that affect the rate of dissolving. Right? There's an overhead with these on there, so make sure that you print it out and look at it. So with the speed of dissolving, there are 3 factors. Factor 1, okay, we could crush the solute. Crushing the solute, why would that make things speed up more? What it does is it increases the surface area. That helps because if you look at our crystal lattice here, right now water molecules can only attack the outsides of it, and the ones in the middle are protected. If we were to crush this up and spread it out evenly on the counter, now the water would have access to all of the solute and it could dissolve it more quickly. The second thing that could increase the speed of dissolving is called agitating the solution. Most often, what this is referring to as stirring. And why stirring helps to dissolve more quickly is it brings fresh solvent to the crystal. So right here, if we were attacking this crystal, all the water molecules around it would become saturated, and there would be a bunch of water up here that is not. By stirring it, we remove the saturated waters and we bring in fresh solvent. The last one is temperature. Increasing the temperature, just like it always does, increases the speed of molecules. The faster the water moves, the more often it can collide with the crystal structure, and the faster that it gets dissolved. Right? So you can crush the solute and increase its surface area, you can agitate it and bring fresh solvent, or we can increase the temp and increase the number of collisions. I hope this helps with what you were doing, and if you have any questions, feel free to stop.